In this video, I'd like to share with you how we can use a graphing calculator, specifically the TI Nspire, to fit a sine function to some sample data. Now, before we get started, let's just clarify a bit of the instructions. I'm going to use the informal definition that we practiced with class last week. I'm going to change some of these letters. Instead of omega, I'm going to use the capital letter B for our horizontal stretching value, and instead of phi, I'm going to use the value or the letter C for a horizontal shift. And also it's worth noting that I'd like to rewrite this with a double set of parentheses. By doing so here, when we get to the very end and we try to identify our phase shift, we don't have to worry about phi divided by omega. We can simply identify that as C. Now, we can change some of the other letters throughout the instructions as well. And this particular step, number 3, might be helpful in recognizing a simple algebra step. Last week we were identifying t, the width of our period, as 2 pi divided by b. Well, if we solved for b by itself, since we're going to need a numeric value for b, we could also solve for it by taking 2 pi and dividing t. This period width, or the width of one cycle of the graph, should be visible to us once we graph these data points. And one last thing before we get too far, I just recognized that they're using the capital letter B for their vertical shift. I want to switch that to D. And so we're going to determine D at this next point. All right, so we have this set of data on the right-hand side. This data shows a record of the number of major hurricanes that have occurred within a given decade since the 1920s. So for our first data point, the decade from 1921 to 1930, there were 17 recorded major hurricanes. Between 1931 and 1940, 1931 and 1940, there were 16 major hurricanes recorded, and so on down the line here. What I would like to do first is to get these data points into the calculator so that we can at least see the behavior of these values from a visual perspective. And the recommendation here was to use, rather than an x value of 1921 or 1930 or anything like that, we're going to use an x value of 1 to represent this first decade, 2 for this second decade, and so on. So when using the TI Nspire, we're going to turn them on and make sure that we get to our home page and follow the instructions that I provide here. For those of you that are using a different calculator, maybe a TI-84 or some other device, we can sit down and look at it specifically, but you have to be able to create lists in your calculator, similar to how I'm creating lists in this one. For the TIs, though, make sure that you select a new document, and we will add a list and spreadsheets page. Now, before I enter any data into this spreadsheet, I like to label my axes, if you will, or my lists. So I'm going to give the letter X here for the x-axis, the decades. I'll press the tab key, and I'll call this one H for hurricanes. And this mimics the description that we were given here on this set of data. Now, when I move my cursor down below, notice I skipped this line where there's an equals. This is reserved for functions that would create data points. But now I'm going to skip down here to where my data is, and I'm going to enter a series of values. I'll just use the keypad here, and after I enter a number, I'll press the Enter key, and that'll move me right down the list. We have 9 decades, so I'm going to enter numbers 1 through 9. Now I'll use the up arrow to get back up to the top row, and I'll record the next set of data. I'm going to pause the video and put the numbers in. Okay, so now I have all that data entered, and it's important to double check, make sure that your A column and your B column have the same dimensions, or they have the same number of entries in them. And we're in good shape here. Now the next thing that I have to do in the TI Nspire is I have to create another page to this document. This time when we add the page, we're going to add a data and statistics page. So I'll press the control key on the keypad and then the document page right here. This will add, I'm sorry, the document key. This will add a new page to the document. We will tell the calculator that we'd like to add number 5, a data and statistics page. And all of the data points that we just typed in our lists have now shown up here, but there is no order to them. So if we move our cursor to the bottom of the screen and click along this empty space here, we can indicate that we want X, the decades, along the X-axis. Then move our cursor to the left-hand side of the screen, click on the Y-axis, and we'll display the hurricanes, the number of hurricanes, along the X-axis. And now hopefully you can see that, yeah, these data points, while they're not perfect, and a lot of times real-world data isn't perfect, but it does appear that the number of hurricanes that occurred in any given decade seem to follow this sinusoidal or this sine wave. So let's see if we can use the techniques provided in our notes today to find the sine function that fits this data. Okay, first things first, let's determine our A value, the amplitude. Now what's nice about this is that the amplitude is very easy to approximate. It's simply the largest data value minus the smallest data value, the high spot in the graph minus the low spot in the graph, and divide that by 2. I could go back to the graph and look at it, but I can also look at the data points that are here. The largest value was 33, the smallest value was 16. So when I need to compute my amplitude, I'll use the numbers 33 minus 16 and divide that by 2. And it appears that our amplitude, or our A value for this function, is going to be 8.5. So I'm going to start building that function over here now. The function appears to be 8.5 times sine, and we'll fill in the rest in just a moment. Next, I think we'll go ahead and follow step number 2, determine the d value, or the vertical shift of the function. Now, if you think of the original sine function, how it's a wave function that has a midline about the x-axis, the new midline of this particular function is going to be somewhere up in the air here. The middle of the sine function is way up in the air, and according to our graph here, it appears to be right around 24. Now, that would be a good number to guess right at the beginning here, but let's go ahead and check this technique that they're providing to us. The textbook suggests that we add the largest data value and the smallest data value and divide by 2. So our vertical shift d would be 33 plus 16 divided by 2. So that's 49 divided by 2, and that's 24.5. So if we were looking at our picture and guessed 24 as our midline, that would have been a pretty good guess. Algebraically, the recommendation brought us out to a result of 24. So at the end of the function, we will have plus 24.5. Now here in the middle, let's figure out what comes next. Okay, let's go for our b value next. In order to determine b, we'll take the period t and enter it into this function. So we'll take the number 2 pi and divide it by t. What makes this part a little bit tricky is that identifying the beginning and the end of the sine curve could be a little bit difficult to identify with our data. But as you recall, a sine curve looks something like this, and this is what one period of the sine function looks like. So when we go back to the calculator here in just a second, what I'm going to look for are the data points that might represent, the start of this curve here and the end of that curve. if I could find out how long it takes for that to occur based on the graph, then I'm going to use that as my t value. With my t value identified, then we can calculate our b value. Now, I might be able to identify that here with our data points too, but I'm going to look at the picture first. And actually, one point that I failed to mention is that we don't have to look at the starting point and the ending point of the curve. If you recall from our initial discussions, if we had more than a curve, we could also measure from peak to peak or from valley to valley. And any one of those distances would represent our t. And so when I look at this data, it's a little bit hard for me to see data points that lie exactly on the midline. So I'm not going to follow that one so much, but maybe instead I'll look at these two peak values. Because as it turns out, we have got two data points that have a H result, or the number of hurricanes within a decade, of 33. And so I'm going to make the assumption that those two are both peaks of this sine function, and they happen to have a distance of 5 decades, from 4 to 9. So I'm going to say that t is equal to 5. Now, if t is equal to 5, then we know that our b value would be equal to 2 pi divided by 5. And we'll enter that result here, 2 pi divided by 5. This is getting a little bit tight, so I'm going to spread my ink out a little bit. Hopefully you left yourself enough room to write your own function. Okay, that's a little bit better. Now, the last component that we need is our c value, the horizontal shift. Now, if you ask me, I think we can simplify step 4 quite a bit. We don't need to divide a period into subintervals. We don't need to complete the division of two unknowns here at this point. Just recall that any sine function has a series of peaks and valleys, and what I would like to do is I'd like to focus on this initial peak for just a moment. Now, the high point of a traditional sine function occurs here at this data point 1, 1. So this x value of 1 is really important. So the peak of a unmodified or untransformed sine function occurs when x is equal to 1. If we look at our graph here, the first peak of the graph appears to be right here at an x value of 4. So the peak should have occurred when x was equal to 1, but now the first peak has occurred when x is equal to 4. So if you ask me, that appears to be a horizontal shift of 3 to the right. So I'm going to say that the c value is equal to 3. So if you'd like to try to read through the instructions here in step 4 and make sense of it, then please by all means do so. But again, here, since we're just trying to make a good educated guess at this point, let's go ahead and just use our common sense and identify this c value for what it is. Now the c value is 3. This was a rightward movement of 3, so I'm going to write minus 3 as the function. And now at this point, all we have to do is check to see how good our guess was. Does this function seem to model our data? Now, if it does, if it's an accurate model for our data, then we could potentially use this to predict future events, or we can use it to perform some other analyses of interpolated data, so what's happening actually in between the data points. So let's go ahead and check this out. All we have to do is go back to our calculator, and what I would like to do is press the menu key and analyze the graph, and let's go ahead and plot that function. Now I think I've got a function stored in F1 already, so that's why mine's saying F2. Yours is most likely going to say F1 on the screen. So let's go ahead and enter what we've got. We've got an 8.5 times a sine function, and I have 2 pi divided by 5. I pressed the control key and then divide. That's what created this fraction. I'll start another set of parentheses, and on the inside we'll write x minus 3 for that rightward shift of 3. And I'm running off the screen. Let me see if I can move this. It's not going to let me right now. So x minus 3, and off the screen I'm typing plus 24.5, and I'll press enter. And there you have it. So here's the function that we guessed, that we well, it was an educated guess, but we thought would model the data, and that appears to be a pretty good fit. It's not perfect, but it's pretty good. It kind of looks like maybe this this whole graph is shifted too far to the right. So if we wanted to fix this, if we wanted to make some changes, we can make that happen. If this curve is shifted too far to the right, and if we want to just slide it back to the left, maybe to get closer to these data points, we can do that by modifying our C value. If maybe we think that the curve should be a little bit taller, then perhaps we can change our vertical stretch, this 8.5 value, and we can mess with it. Now, if your graph didn't appear to fit at all, but you did follow all of the steps along with me, check to make sure that your calculator's in the correct setting. We want radians now. As you'll find with a lot of our real-world numbers, radians appears to be a better fit. It's a better look for our x-axis. And if you were nowhere close or you got completely lost along the way, try replaying parts of the video to make sense with where you were, and we'll give this a try when I see you tomorrow. In the meantime, I would also like to see you continue to practice sketching some graphs by hand. So do make sure that you are practicing this. I've got 2 graphs that I'd like for you to complete by graphing using degrees, and 2 that I'd like for you to complete using radians. And on each of those, I suspect you can sketch those graphs by using key data points and adjusting your scale to fit. If you're not happy with the scale that I've provided for these radian measures, then by all means scribble them out and use your own. Now, while I was scrolling there, I did realize, and I forgot to mention too, that I did provide a modified result. So after playing with the numbers a little bit more, I think I ended up with this result for a graph that was pretty close to fit. But we'll talk more about that fitment, and then why I have 2 images over here on this graph on the right. Please let me know if you have any questions. Thanks.